The distance between any two consecutive points that vibrate in phase on a wave is the wavelength, right? So 1.1, our answer here is going to be B, right? Because the distance between any two consecutive points that vibrate in phase is wavelength, right? And then off to 1.2, a wave moves past a fixed point at a speed of x meters per second. If the speed of the wave stays the same and the frequency of the wave doubles, then the wavelength of the wave will, A we have half, double, remain the same, and increase fourfold, right? So here, let's conceptualize, right? We know that we have V being equals to frequency multiplied by wavelength. So it is said that the frequency has been doubled, right? But then the velocity or the speed stayed the same. So what happened to wavelength, right? So let's say our initial frequency was 2 hertz, right? And then our wavelength was 2 meters. So V would be 2 multiplied by 2, which is equals to 4 meters per second, right? But then now it is being said that the frequency has been doubled, but the velocity remains the same, right? So if the frequency is doubled, then we're going to have V being equals to, so instead of 2, we're going to have 4 hertz, right? And then multiply by, we need V to still be 4 meters per second, right? So the wavelength now has to be 1 meters so that the velocity remains being 4 meters per second. So you can see it with this illustration that if we double the frequency and you want the velocity to stay the same, you have to halve the wavelength, because here we had a wavelength of 2 meters to get a speed of 4 meters per second. But then now that we have doubled the frequency, we only need a wavelength of 1 meter, right? So that's how it works. This might be a bit challenging, but then if you put some thought into it, you will realize that it's not too complicated. And then now we have 1.3. 1.3 saying that the diagram below represents two sound waves, A and B. Which one of the following combinations that compares the frequency and loudness of A and B is correct? Let's look at option A. It is saying that the frequency of A is greater than that of B, right? So let's go on our sketch and see if that is true. So from here to here, we have one completed wavelength. And then from here to here, we have one completed wavelength. So if we assume that on the x-axis we have time, then that will tell us that the period of A and B is the same. And then if the period of A and B is the same, then the frequency should be the same. So now the only options we're looking at is option C and option D, because they're saying that the frequency of A and B, they are the same, right? And then let's look at the loudness, because that's the other criteria we have. Option C says that the loudness of sound wave A is greater than that of B, right? What is loudness related to? Loudness is related to the amplitude. We can see that the amplitude of B is greater than that of A. So our answer here for 1.3 is actually D, because the frequency of A is the same as the frequency of B. But then the loudness of A is less than the loudness of B because of the amplitude. Sound wave B has a higher amplitude. And now off to 1.4. So we have 1.4 here saying that doctors use certain equipment to check on the health of unborn babies. This equipment uses, we know fully well that this equipment uses ultrasound, right? So our answer for 1.4 is going to be option C. A pulse is a single disturbance in a medium. A pulse is a single disturbance in a medium. It doesn't get easier than that, right? So that's the answer for 2.1. A pulse is a single disturbance in a medium. And now let's move to 2.2 and see what we can do here. So the diagram below shows two pulses, L and M, right? As we can clearly see on the left hand side, right? We have pulses L and M traveling in opposite directions in a row. The amplitude of pulse L is unknown, and that of pulse M is 7 centimeters. And then the two pulses, they meet at point X. Point X is right here, right? And the resulting amplitude is shown below, right? We have a resulting amplitude of 4 centimeters. And then the question that follows, 2.2.1, what type of interference takes place at X? What type of interference takes place at X? So let's just cover the basics, right? If we have two pulses, one being above rest position and the other one being below rest position, then they interfere destructively, right? So we have what we call destructive interference, right? That happens all the time when we have two pulses, one being above equilibrium and one being below equilibrium, right? And then if we have two pulses both being above the line of equilibrium, then we're going to experience constructive interference, right? We're going to experience constructive interference, right? But then as you can see here on the example we have two pulses, one being above the equilibrium and one being below the equilibrium. So the type of interference that is going to take place in 2.2.1 is going to be destructive interference, right? So our answer for this question will be destructive interference. And then now let's do 2.2. So 2.2.2 is saying that why is it possible to apply the principle of superposition at X, right? So we can only apply the principle of superposition when two pulses occupy the same space at the same time, right? So that's the condition we have for the principle of superposition. The two pulses occupy the same place at the same time, right? And then let's move to 2.2.3. So 2.2.3 is saying let's determine the amplitude of L, right? We're given the amplitude of M and the resultant amplitude after they meet, right? And we know that the resultant amplitude will be equals to the amplitude of L plus the amplitude of M. The resultant amplitude will be minus 4, right? Why are we putting a minus sign? We put in a minus sign because the resultant is below equilibrium, right? And that will be equals to the amplitude of L and then plus the amplitude of M. The amplitude of M is also below the position of equilibrium, right? So we're going to substitute it with a negative sign. So we're going to have minus 7. So if we take minus 7 to the left hand side, we're going to have minus 4 plus 7 is equals to the amplitude of L. So 3 centimeters is equals to the amplitude of L, right? And just like that, we've determined the amplitude of L. And now 2.2.4. 2.2.4 is saying that in which direction does pulse M move after the two pulses pass each other, right? Either to the left or to the right. If these two amplitudes meet at X, then that tells us that M is moving to the left, right? So the answer to 2.2.4 will be to the left, right? Pulse M will continue moving to the left while pulse L continue moving to the right. The following wave pattern is produced by a transverse wave that takes 4 seconds to complete one vibration. So from that, we know that the period of our transverse wave is 4 seconds, right? And then the first question, 3.1, is saying let's define the term transverse wave, right? So a transverse wave is a wave where the particles of the medium vibrate at right angles to the direction of motion of the wave, right? So as you can see here on the left hand side, the particles are going up and down while the transverse wave moves from A to B, right? So they're moving at right angles to the direction of the motion. So that's the definition for a transverse wave. And then 3.2 says let's determine the frequency of the wave, right? So we've already deduced that the period is equals to 4 seconds, right? Why are we saying the period is equals to 4 seconds? Because we have been told that it takes the wave 4 seconds to complete one vibration. So we can say that the frequency is equals to 1 divided by the period, right? That is just 1 divided by 4, which is equals to 0.25 hertz, right? So the frequency of this wave is 0.25 hertz. And then now off to the next question, 3.3. So 3.3 is saying that if the speed of the wave is 0.05 meters per second, let's calculate the value of x in millimeters. So let's go and look at x, right? So x runs from this point to this point, right? So let's look at x in terms of wavelength, right? So from here, if we keep going to this point, we have one wavelength, right? And then from that point to this point, we have half a wavelength. So we can say that x is equals to 1.5 wavelength, right? We can see clearly from the sketch that x is indeed 1.5 wavelength. So if we calculate the wavelength, then we can just substitute the wavelength here and determine the value of x in millimeters, right? So let's go ahead and do that. We are told that the velocity is equals to 0.05 meters per second. We know that the period is equals to 4 seconds and the frequency is equals to 0.25 hertz, right? So we can say that the velocity is equals to the wavelength divided by the period. So what is the velocity? The velocity is 0.05, and then the wavelength is what we're looking for, and the period is 4 seconds. We can go ahead and cross multiply. So we're gonna have wavelength being equals to 4 multiplied by 0.05, which is equals to 0.2 meters. So wavelength is equals to 0.2 meters, right? So now we can go ahead and say that x will be equals to 1.5 multiplied by 0.2, right? What the wavelength is. And then if you compute that, we should get 0.3 meters, right? But then let's not forget, our question says that we need the value of x in millimeters and not in meters, right? So we're just going to say that x is equals to 0.3 multiplied by 1,000, right? So this should be equals to 300 millimeters. So that's how we essentially solve this kind of problems. And now let's move to the next one, 3.4. 3.4 is saying that how long in seconds does it take for a particle to move from point A to point B, right? Let me show you something. So it takes the particle 4 seconds to move one wavelength, right? So from A up to this point, it takes 4 seconds. So we have the first 4 seconds, right? And then from here up to this point, we take another 4 seconds, right? That's the period of the wave. And then from that point to this point, that's a third 4 seconds. And then from this point to this point, we have half a wavelength. So that is going to take 2 seconds, right? So we have the time we are looking for being equals to the first 4 seconds, the second one, the third, and the 2 for the half wavelength we have at the end, right? So that will be 4, 8, 12, 14. So we have 14 seconds, right? It is the time we take to move from point A to point B. Region of high pressure in a longitudinal wave. A compression is the region of high pressure in a longitudinal wave. That is the answer to 4.1.1. So now we can move to 4.1.2. So 4.1.2 is saying let's use the diagram to determine the wavelength of the wave, right? Let's use the diagram to determine the wavelength of the wave. So how do we determine the wavelength of a longitudinal wave? It is the distance between two compressions, right? The distance between two compressions. So let's go to our sketch and do some analysis. So from this compression here at A to this compression here should be one wavelength. And then from that compression to this compression shall be our second wavelength, right? And from that compression to this region of low pressure here that we have shall be half a wavelength. Now we can see that 24 centimeters is equals to 2.5 wavelength, right? So we can go ahead and divide both sides by 2.5 in attempt to find the wavelength, right? And then if we do that, we get wavelength is equals to 9.6 centimeters. So the wavelength of our longitudinal wave is equal to 9.6 centimeters. And then now to 4.1.3, the question says that let's determine the period of the wave if it takes 1.5 seconds for a particle to move from A to B. So it takes 1.5 seconds in order to travel 2.5 wavelength, right? That is the information we have. It takes 1.5 seconds to travel 2.5 wavelength, right? And we want the period. So let's go back to the definition. What is the period? The period is the time it takes to complete one wavelength, right? And then in this question, we're being told that to complete 2.5 wavelength, we take 1.5 seconds. So in order to find the period here, we're going to say 1.5, the time it takes to complete 2.5 waves, divided by 2.5, right? And then if we do that, we're going to be able to find the time it takes to complete one wavelength. And then if we compute that, we're going to get 0.6 seconds, right? So the time it takes to complete one wavelength is 0.6 seconds, right? You say the time it takes to complete 2.5 waves divided by 2.5 waves, and then you will get the period. And then now off to 4.2. Two boys conducted an experiment to determine the speed of sound in air. They stood 500 meters away from a mountain, and the boy fired a toy gun directly towards the mountain. And then while the other boy fired the toy gun, another boy simultaneously started a stopwatch. It then recorded the time to hear the echo. The experiment was repeated 3 times and the readings were recorded. Right, and then the first question, 4.2.1, how is an echo produced? An echo is produced by sound waves reflecting off a surface, right? So an echo is produced by sound waves reflecting off a surface. And now 4.2.2. So 4.2.2 says, let's determine the average time for the above readings, right? So we can say that x bar from mathematics is equal to the sum of all x values divided by the number of terms, right? So here we have 3.01 plus 2.95 plus 3.04, right? So we're just adding up the time taken for the 3 experiments, right? And then we divide everything by 3 because we conducted 3 experiments. So the average time it took sound to travel to the mountain and back to the boys is 3 seconds. And then let's go and do the next question, 4.2.3. It's saying let's calculate the speed of sound. So we need velocity, right? But then we have the distance. We know that the sound waves travel 500 meters to the mountain and 500 meters back to the point, right? So we can say that our distance is 500 plus 500 because the sound waves travel to and from the mountain. So our distance will be 1000 meters. But what is our time? We just calculated it in 4.2.2, right? Our time is 3 seconds. So here we can go ahead and say that the velocity is going to be equal to the distance divided by the time. And then the distance, that is 1000, and then the time is 3, right? It only takes 3 seconds. And then if you compute that, you're going to get 333.3 recurring meters per second, right? And now off to the last question, 4.2.4. It says that how does the speed of sound in water compare to the speed of sound in air? Choose from greater than, less than, or equal to. We know fully well that it is greater than, right? It is greater than. That is because water is more dense compared to air. In the introduction of electromagnetic radiation, you should have talked about the fact that it behaves as a wave and as a particle. That is what is meant by the term the dual nature of electromagnetic radiations. It shows properties of both wave and particle. In grade 11, there's a topic on the wave nature of electromagnetic radiation. And then in grade 12, you're going to explore the particle nature of electromagnetic radiation. Right, let's do 5.2. So 5.2 says that a particle has 3.98 times 10 to the minus 13 joules of energy and has a wavelength of 5 times 10 to the minus 13 meters, right? And then the first question, 5.2.1, says, what is a photon? A photon is a packet of energy in which light travels. A photon is a packet of energy in which light travels, right? Let's move to 5.2.2. 5.2.2 says, what is the speed of a photon, right? If it is a photon, then we know that it's a packet of energy in which light travels. And then what is the speed of light again? The speed of light is c is equals to 3 times 10 to the power 8 meters per second, right? Nothing travels faster than light. And then 5.2.3 is saying that by means of a calculation, let's show that the above particle is a photon. By means of a calculation, let's show that the above particle is a photon. So let's jot down the information we have so that we can see how we can potentially solve this problem. So we're given the energy, right? It is said to be equals to 3.98 times 10 to the minus 13 joules, right? And then we're given the wavelength. It is said to be equals to 5 times 10 to the minus 13 meters. Right, and then the question is saying that by means of a calculation, let's show that the above particle is a photon. How would you know that a particle is a photon? If it's traveling at a speed of 3 times 10 to the power 8 meters per second, you would know that that particle is a photon, right? Nothing travels at that speed except for photons, right? So you're looking for C in 5.2.3. If you can prove that C is equals to 3 times 10 to the power 8 meters per second, then beyond reasonable doubt, we would know that that particle is a photon, right? So let's go ahead and see what we can do here. We know that the energy is equals to Planck's constant multiplied by speed of light divided by the wavelength. Right, and then what is the energy? It is given to us. We have 3.98 times 10 to the minus 13. And then what is Planck constant? 6.63 times 10 to the minus 34. And then multiply by c, speed of light, right? That's what we're looking for. We're trying to prove that it is equals to 3 times 10 to the power 8. If that is the case, then that particle is a photon, right? And then the wavelength, we have 5 times 10 to the minus 13, right? So now the physics is essentially done. We just have to solve for C, right? So let's take it easy. Let's not do any complicated math. Let's just go ahead and cross multiply. So if we do that, we're going to get 3.98 times 10 to the minus 13 multiplied by 5 times 10 to the minus 13. And then this is going to be equals to 1 multiplied by 6.63 times 10 to the minus 34. Everything multiplied by C, right? And then from here on, we're going to divide both sides by the coefficient of C, because we want to isolate C. Is the value of C that we're looking for, right? So we're going to divide the right hand side by 6.63 times 10 to the minus 34. So this number and this one, they cancel out. And then on the left hand side, we have to divide with the same number, right? So that we maintain our equality. So if you put what's on the left hand side on your calculator, you can get 3 times 10 to the power 8 meters per second, because we're looking for speed, and then it's equals to C, right? We can conclude that our particle is indeed a photon because it has a speed of 3 times 10 to the power 8 meters per second, right? let's move to 5.3 and see what we can do here. So we have 5.3, which is saying, will a photon of ultraviolet light have more energy or less energy than a photon of gamma rays? Let's give a reason. So a photon of ultraviolet light will definitely have less energy, right, compared to gamma rays. We know that gamma rays have the most energy, I think, followed by X-ray and so on. So ultraviolet will have less energy compared to gamma rays. And they're saying we must give a reason, right? We know fully well that the energy is equal to Planck's constant multiplied by frequency. That's another formula we have, right? So we're saying gamma rays have the most energy because they have the most frequency compared to ultraviolet light. So we're gonna say less energy because ultraviolet light, right, has less frequency. It has less frequency compared to gamma rays, right? You have to write in full. You don't have to write it like the way I'm doing here. I'm just doing that to save time, right? Or you can even go ahead and talk about the frequency, about the wavelength I meant, because we know that energy is equal to H multiplied by C divided by wavelength. This might be a bit confusing for a few, but bear with me here, right? You can say that ultraviolet light has less energy because it has a higher wavelength, right, compared to gamma rays, because energy and wavelength, they are inversely proportional to each other. When wavelength increases, energy decreases, right? And the last question, 5.4 says, let's name the type of electromagnetic radiation that is used to study animals at night. That's quite an easy one, right? It's infrared.